Uh, Hi everyone. Can you hear me? Can someone please confirm if I am audible?
Yes, sir, you are audible.
Thank you. So, I welcome you to this course. I am Om Maheshwari. I am from IIT Gandhinagar, and I am one of your TAs for this course. I will be taking live sections every week for 2 hours at on Tuesday, every Tuesday from 6 to 8 p.m. Okay. So, I suppose you will follow this course throughout the end and make use of these live sessions. So let us start. So I'll solve some of the questions which may help you with your assignments throughout this course. So these questions are from some of your previous assignments. So I will solve some of them so that may help you solve uh, this week's assignment. Okay. So here let us go for the first question. And if you have any doubts, please feel free to stop me in between. So here in this question, we have a voltage regulator and it has specification Vs is 24 volts. So let us write that Vs is 24 volts, Rs is 300 ohms, and RL is 1 kilo ohm. And the Zener diode has breakdown voltage of 18 volts. So plus minus 18 volts. So what we have to find the current through the Zener diode when its breakdown voltage is given. So it is a very simple question. So when the Zener diode breaks down, the question is what current will flow through it. So that voltage across is plus minus 18 volts. So that means the same voltage will be across this also 18 volts. So we can find the current through this resistor. Let's do 18 by 1K. Let's say 18 milliamperes. And okay, so if we see, so here it is 24 volts, here it is 18 volts. So difference is 6 volts, right? So across RS, we have plus minus 6 volts. So what will be the current through RS? IRS equals to 6 upon 0.3 kilo ohm. I'm writing in kilo ohm, so I get in milliamperes. So that will be 20 milliamperes. So now if we look at our circuit again, 20 milliampere is going here and 18 milliampere is going here. So that leaves us with 2 milliampere current in the Zener diode. So that is why we will have answer, our answer to be 2 milliamperes. Is there any doubt in this question?
Sir,
Yes.
sir, while converting the diode into terminals
Sorry, can you repeat? You
plus or
lost your
minus
voice
how,
in.
while converting the Zener diode into an 18 volt source,
Yes.
how can we determine its positive and negative terminals?
So if okay,
How to
good question. Yes, I'll tell you. So a Zener diode operates in reverse bias. So uh, when it's breakdown, so let's say this is V, this is I. In forward bias, it behaves like a normal diode. A Zener diode behaves as a normal diode in forward bias. In reverse bias, it
okay, okay,
maintains a certain voltage, let's say VZ, and then it breaks, and then it maintains this voltage across it, no matter how much the current you increase. So that is why I applied the polarity such that it is reverse biased. So this term, this so If I would have applied positive here and negative here, it would have become forward bias, right? Like in a
Yes.
normal diode, plus minus gives you forward bias, and opposite of this, minus plus gives you reverse bias. Is it clear now?
Okay, sir. Thank you.
Okay. Any other questions? If not, let us go towards the next question. Yeah. Okay. Okay, let me see the chat once. Okay. 1 second. Adil, is this regarding week 1? Adil, these are previous year's assignment. This I have combined week 0 and week 1 for this session. So these questions are initially from week 0, then I have week 1 questions also. Raja says answer is D. So Raja answer is A. Oh, sorry, C. Okay. Let us go towards the next question. Okay. An ideal op-amp has the following characteristics. Okay. Good question. So what is an op-amp? Okay. So op-amp is a circuit where if you give some input VD, it amplifies it by A times VD, right? If this is plus minus VD. Losing connection, yes. Okay. So for any amplifier, so what do we want? So let's say you are getting some signal from a source. Let's say you have some sensor. Let's say a sensor. Okay. Now you want to read this signal. You will take, let's say this is the Rn of the amplifier. You have some amplifier block. This is R out. And you have some load, RL. So while reading the signal, what do you want is that all of this signal should be, let's say, if this is 5 millivolt, you want all of this 5 millivolt across this amplifier, right? So, uh, okay, let me not draw it like this. Draw it like this. Let's say this is R's, yes, and this is Rn. Okay. So, uh, if uh, if let's say Rn is very low, so very less voltage will drop here, and out of this 5 millivolt, let's suppose only 2 millivolt is dropped here. But we do not want that. So Rn, if Rn tends to infinity, all of this voltage will drop across this. So uh, then that is why we need high input impedance. Or since it is an amplifier, we want gain to be very high, and R out should be less. R out should be less such that again the similar concept. So if R out is very high, all of the output voltage V out will drop across R out. We do not want that. We want it to drop across the load. So R out should be approximately 0 so that all of the voltage drops across the load. That is why the answer is A. So this was a theoretical question. Any doubts here? Anas, Paresh, Raja. Yeah, you have right answers. Good. Okay. So let us see the next question. Okay. So can anybody guess what circuit is this? You may have seen it earlier. Okay. Paresh says differentiator. Lata says integrator. Okay, high pass circuit. Good. Okay, so it is a differentiator or high pass. Both are same thing. Okay. Raja, do you have a question? You have raised your hand. Okay, maybe not. So I'll continue. Okay. So this is a differentiator. So I'll not go into the why it is a differentiator because for that I will need to go into the transfer function that you may see in any analog course. But yeah, this is a differentiator. So, but if we had a circuit like this, if we have a resistor, we, and here it is a capacitor, then it is an integrator. So, anyways, so now the question is, what will this circuit do? So we are giving a square wave input. We have a square wave input. So what is the differentiation of a square wave? So wherever there is slope change, we will get a spike, right? So okay, the differentiation of this voltage. So that is why this is spike. We are doing d by dt. This is time. This is time. So why I've done this? So there is like a slope change of very high slope change. That is why we are getting a spike here. And here the slope is constant. That is why we are getting zero signal. So d by dt is just the slope of every part of this circuit of this signal circuit. That is why we are getting a spike or an impulse signal. So answer is D. Okay, let me see the chat. Yes, answer is D. Bansari says the record link of these recorded lectures of the session. I think you can get the, there will be a sheet that will be shared with you in your course website itself. There you will find the recordings of all the lectures that the TAs take and also the slides also that the TAs have made. So if you do not get them, I'll share my email again. So this is my email. If you do not get the recording, please email me and I'll share the YouTube link with you. I'll upload this recording in the YouTube. Okay. Okay. Avinash says pulse wave is also known as spikes. Not necessarily, Avinash. This can also be called a pulse. Okay. Let us move on to the next question. For stability of a common emitter amplifier for preventing thermal runaway, which of the following is used? Okay, we'll go to this later. First of all, what is thermal runaway? So If we have a bipolar transistor, yes, okay. So in this, when let's say when collector current IC, when IC is high, then as we know when current is high, the temperature will increase. Okay. Now, when temperature increases, one second. When temperature increases, it increases the reverse saturation current, that is IC naught, which in turn again increases IC. Now, since again IC is high, temperature again increases. So this loop keeps on going until the transistor is burnt. This is called thermal runaway. So, uh, to prevent that, we can have an emitter resistance. So, how does emitter resistance prevent thermal runaway? So, let us say we have a resistor here, RE. So, as soon as this current IC increases, the voltage is dropped across this RE, which reduces the VB of this transistor. And when this VB is reduced, IC is again reduced, right? So in this way, this RE gives a negative feedback. It gives a negative feedback. So since voltage is dropped here, as IC increase, this VBE decreases, which decreases IC. This is how it prevents thermal runaway. Uh, okay. Any doubts here? So if you see MOSFETs also, they also have a similar, what's it called it? RS. So it is drain, source, and gate. They also employ this RS for giving negative feedback and stabilizing the gain of the circuits that are made using MOSFETs. So maybe we'll study them later in the course. But yeah, just for your information. Okay. Mm, Let us see another question. I already take the answer. Let me erase it. Sorry. So this is a very simple question. When transistors are used in circuits, digital circuits they usually operate in. Let us see. Let's just have a MOSFET. So at 5 volt here. Let's say RC. Okay. So uh, in digital circuits, we only deal with 0 or 1, right? 0 or 1. So in which regions of operation can we get those kind of signals from? So what should be, uh, where should this transistor operate to get V out is as either 0 or 1? Or let's say 0 or 1 here represents 5 volts since I've given 5 volts as VDD. So yes, Jagannath and Avinash. So what happens is that when I apply 5 volts here, so this transistor is turned on and the current flows through this transistor and very less voltage drop uh, is here across this transistor. It is approx 0.2 volts in saturation. So we consider it as a 0. So here for getting 0, we are using saturation. And if we apply, let's say, take the darker color. If we apply 0 volts here, the transistor is turned off. That means no current flows through here. So all this 5 volts is available at V out. So for this we use cutoff. Therefore, in digital circuits, we usually operate in saturation or cutoff regions. So it is a very simple concept. Is it clear? I hope it is. Let us move on. Is anybody saying anything? Let me check. Okay, I'll move on to the next question. Okay, number systems. So log 21024 equals to x. What is x? Okay, so it essentially means that 2 to the power x equals to 1024. So can anybody tell me the answer? It is simple. Yeah, 10. Good. So it is just 2 to the power 10 is 1024. This was a very simple question. And yeah, let me just give me a moment. Okay. So yeah, 10 is the correct answer. Okay. So which gates are called as universal gates? Yeah, we know this common knowledge. NAND and NOR gates are universal gates, so you can make any gate out of NAND and NOR. So let me frame a question. So how many? Just tell me how many uh, number of NAND gates to make the following. And or NOR XOR XNOR. Okay. Renuka says two. Let's check this. Two, three, four, four, and five. Okay. So I'll just check. Uh, okay. So for NAND gate, we have a NAND. Let's say A B another NAND. So it is A dot B whole bar, and it will be AB. This is just a NOT gate. Single input NAND gate is a NOT gate. So yes, it is correct. For OR gate, let me see. OR gate we can achieve as, let me see, A bar, B bar, A bar dot B bar whole bar, that is A plus B. This is OR gate. This is AND gate. Okay. So similarly, you can do the others also, and let me just see if this is correct. It's not 1, 2, 3, 4. Yeah, so this is correct. All these are correct. So does anyone want me to draw the rest of them? If not, we will move ahead. Okay, so I'll just share. Let me see from Google itself. Or to uh, so this you can follow. Those who do not know, uh, all the gates are given using NOR gates, and similarly you can see from NOR also. Okay, and try to solve these. Like if you face any difficulty in these, please email me. It's fairly easy. You just have to find the output from each of the gates. So let us go back here. If 125 R is 104 base 5, then the value of radix R will be okay. So let us write it. So what does it mean? Let's say we have uh, 1, 2, 3 to the power of base x. So it means that how do we expand it? It means we write so everything is in multiplied by the power of x. So this is LSB, this is MSB, least significant and most significant digits. So it will be 3 into x to the power 0 plus 2 into x to the power 1 plus 1 into x to the power 2. Whatever you have, let's say we have 4 also in front of it, then it will be 4 into x power cube. This will be your final answer in base 10. So similarly, we'll proceed with this question. Okay, so 125 R to 104 is 5. The value of radix R will be. So let us just expand these as we did earlier. So it is, I'll write this part first. So 5 into R to power 0 plus 2 into R plus 1 into R square. Now this part is 4 into 5 to the power 0 plus 0 into 5 plus 5 square. So if I just write it, it will be R square plus 2R plus 5 equals 25 plus 4. Yeah. So R square plus 2R equals 24. Yeah, plus 2R minus 24 equals to 0. So you just have to solve the quadratic equation. So we will get R equals to plus minus, what do we get? 2, sorry, equal to minus B plus minus under root B square minus 4AC upon 2. So this is A, B, C. We get minus 2 plus minus under root 4 minus 4 into minus 24 upon 2A, sorry, 2 into 1. Will give me minus 2 plus minus the under root 100, so I'll just write it as 10, 10 by 2. It will be 2 plus 10 by 2 and it's 2 minus 10 by 2. Yeah, sorry. So what we will get finally, 8 by 2 or minus 12 by 2, it is 4 or 6 minus 6. So we cannot have negative bases, or the radix cannot be negative, so our answer will be 4. Is there any doubt in this part? Okay, how did I take plus minus 10? Okay, so 4 into 24 is what? 96. This minus and minus will become plus, so 96 plus 4 under root 100. Under root 100 is 10. Sorry, 10. Is it clear, Prajwal? Okay, so let me give you a small question here. Uh, Find R, so that 121 base R equals to 144 base 8. Please tell me the value of R. Need to follow the similar way. It will be R square plus 2R plus 1 equals to 8 square plus 4 into 8 plus 4. Right? This will be 64 plus 32 plus 4. So, 100 plus R square plus 2R plus 1. Yes, Latha, you are correct. It will be 9. So, equation will be R square plus 2R minus 99 equals to 0. And if you solve it, you will get R equals to, okay, you can do one more thing here easily. can write it as r plus 1 whole square equals to 100, or let me write it as 10 square. R plus 1 equals to 10. It implies r equals to 9. So I hope this is clear, right? Okay. So the next question is to minimize the Boolean function f equal to a b c d bar a b c d. Okay. Let us try this. So I will, for those who have not studied Boolean algebra, it's fine. We will be discussing more about this in the coming assignment, but just as an introductory question, we will take this. So how to solve it is, let me just write it to a b c bar d plus a b c d bar plus a b c bar d bar plus a b c d. So okay. So how do we proceed with solving these questions? We take common terms from any of the uh, expressions that we can find, and we try to reduce it as much as possible. So let us see, these two and these two have common ABC bar, ABC bar. So we'll take these two common, and these two and these two, they have ABC common. So we will get ABC bar. We take common, then it is D plus D bar, right? And from these two terms, we get ABC, that's it, D plus D bar. So in any circuit, let's say A plus A bar is always equals to 1, because in digital circuits, since A can be either 0 or 1, right? If A is 0, A bar will be 1, it will always be 1. If A is 1, A bar will be 0, it will always be 1. That is why A plus A bar is 1. So here we will have A, B, C bar 1, or I'll just remove this one, or plus A, B, C. Again, we will do the same thing, A, B, C plus C bar, sorry, C bar plus C. It will be again A, B, this will become 1. So our answer finally will be F equals to A, B. Uh, this was fairly easy. Let me find another question. Okay, I'll give another simple question. You tell me the answer. Okay, let's do A, B, C plus A bar plus A, B bar, C. Please tell me the answer for this first, and if you are able to solve it, let's see. Yes. Uh, Rajwal, you are incorrect, and Siva, I think you are correct. Okay, so let us try to solve this. Again, what we will do is we will take common from these two. A, C, we will get B plus B bar. This A bar remains as it is. So it is AC plus A bar. Now, okay. Again, okay. So, hmm, how do I tell this? So, this will be A bar plus C. Let me find what it is called. Uh, so, now the question will be why, how we came to this, right? Okay. So, so let us take another simple example. If we have A, uh, A plus B and A plus C. If we solve it, we will get A, A into A is A plus AC plus AB plus BC, right? So if I take A common, A, 1 plus AC plus AB plus BC. So this all will be 1 only, so it will be A plus BC, right? So in a similar way, what we can do is for this part, let's say plus A bar plus AC we have, right? You can also write it as written as plus A bar and A bar plus B. So here, if you see the difference, we had A plus BC. So instead of A, here we have A bar plus AC. So you are writing A plus BC as A plus B. And I write it with another color. We are writing as A plus B, A plus C. So this we will write as instead of A, we will have A bar. Instead of B, we will have A. C is as it is, and again A bar plus C, right? Instead of plus C. Now A plus A bar is 1. A bar plus C, it is A bar plus C. So we have AC plus A bar equals to A bar plus C. Um, is it clear, Ashwini? Okay. Anybody else has any doubt in this? Okay, fine. Let us move ahead. Find the gray code of the binary number. So, so this is not very important as of now, maybe because we have not studied the uh, number systems yet. But I'll just tell you how to convert gray binary to gray. For doing binary to gray, Let's say we have any number 101010. So if this is binary, what is gray of this? So we write MSB as it is, that is 1. Then we do XOR operation between the two digits and then write the answer. So 1 and 0 XOR is, so let me write A, B XOR 0 1 1 0 1 1. So XOR is 0 1 1 0. So whenever A and B are unequal, we get 1. So we get 1 here, again XOR, we get 1, XOR, we get 1, and 1, and again 1. So the gray conversion of this number is this. So is it clear? The method, we write MSB as it is, and then we just keep doing XOR of the two digits and then write it here, right? So I'll let you do this. Please let me know the answer. Yes. So we have 101101. So we'll write MSB as it is 1. 1 and 0 XOR is 1. 1 and 0 XOR is 1. 1 and 1 XOR is 0. 1 0 XOR is 1. 0 1 XOR is 1. So the answer is which one? D. Is it clear? Yes, so most of you have answered correctly, I think. Let us see the next question. The following circuit diagram is functionally equivalent to which gate? So I'll wait for you to answer. XNOR. Okay. So here what we have a single input NAND gate. So if we give A as input, we'll get A bar here, and here we'll get B bar. Okay. Here inputs are A and B. Now again NAND of A bar and B bar. So A bar dot B bar whole bar. Here A dot B whole bar. Now again NAND. So F will be A bar dot B bar whole bar dot A dot B bar whole bar. Right. So if we use De Morgan's law, it says A dot B whole bar equals to A bar plus B bar, and A plus B whole bar equals to A bar dot B bar. So we will use the first one here. So for this is A for us and this is B. We will get A dot B bar plus A dot B whole bar 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 bar. Now this 2 will negate and we will get A bar dot B bar plus A dot B, which is XNOR. Any doubts in this? Okay. Consider the below circuit. The diodes are ideal. The power supply is of 5 volts. The inputs are 0 volt for logic 0 and 5 volt for logic 1. Which logic operation is performed by the circuit? Just a minute. Okay. Does anyone have any answer? And gate. Okay, Renuka. I think you are correct. So let us see how. So what we have is A, B, C, and we have to find, let's say, V out. So 0, 0, 0. So if we give 0, 0, 0 to here, then this diode will be on. So this will be reverse bias. All three will be reverse bias, right? So this node will be at 0. We will get 0. So we see like uh, even if these are 1, if this is 0, this diode will be on and we will get 0 volts here. So if any of these cases arise, whenever any one of the inputs is 0, V out will be 0. Let us say that is not the case and all of the inputs are 1. When all of the inputs are 1, this is reverse bias. Oh, sorry, earlier I spoke reverse bias, I think, but sorry, that was forward bias. So when we apply 0, here it is high, it is low, that would be, if we apply 0, that would be forward bias. So in the earlier, all these cases, diode was forward bias. But here in this case, when all are 1, when all are 1, all are reverse bias. So these are essentially open circuits. So let's say if this is 5 volts here, no current flows through this, and all the 5 volts is at V out. When it's 1, 1, 1, V out equals to 1 or 5 volts. Logic. So if we, so how, when does this happen? 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, 1. It is typically an AND gate. That is the similar case here when any of the inputs is 0, output is 0. When all the three inputs are 1, then output is 1. This is an AND gate. Rama Devi, is it clear? You had written NAND. Okay. Anybody else has any doubt in this? If you want, I can repeat this part. So you just have to remember this. If this is high, this is low, it's forward bias, essentially open circuit or short circuit. And if this is low, this is high, reverse bias, open circuit. This is the only thing that you have to remember. Then you can, so this is called diode transistor logic. And we are making gates using this logic. Okay, so this is how we make a 3-input AND gate using diode transistor logic. 3-input AND gate. Okay, so if this is clear, let us see the next question. Okay, so it looks very scary when we see it at first time. Let us see how it turns out to be. In the given circuit, RC is 2 kilo ohms. Okay. RB is 1 kilo ohm. Okay. This is 5 volts. 5, 5. V out when VA is 0 and VB is 5. Okay, fine. So, okay, how should we do this is let us just try to find what these individual gates are. So, this is one gate, let's say name it 1. This is another gate, 2, and this is another gate, let's call it 3. So, what is the first gate? Okay, let's see. So, here, F here. So, let us just make a truth table and see which gate is this. Can anyone tell which gate is this? Hmm, yes, nor. So let us see each of the condition when we apply 0 and 0. So if we apply 0 here and 0 here, both of these diodes are off. Then this transistor is also off. Since here there is no bias, then all this 5 volt, no current flow is flows, and all this 5 volt is at output F is 1. Similarly, let us see 1, 1, 0, 1, 1. So when any of this is 1, let me write again. Let's say this is 1, this is 0, or any of them is 1. Whenever any of them is 1, this 1 will reach here, right? That means this will diode, this we have VB positive, this transistor will turn on. Just a moment. Okay, so when any of these are on, this transistor will turn on and all the voltage will drop across this RC and we will get 0 here. 0, 0, 0. And this is NOR. Okay, now try for second one, this circuit. Tell me which circuit it is. Renuka has written NAND and Dr. Amisha Shah is saying and. Okay, let us see what it is. So we will do a similar analysis. Just draw it quickly. Again, let us see. When this is 0 and 0, both of these are on. Or let's say when any of this is 0. In all of these cases, when any of these cases 0, any of the diode is turned on. So when any of the diode is turned on, we get a clear path here, and that will uh, turn on this transistor. We get some voltage here, and that will turn on this transistor, right? Maybe I spoke opposite. Sorry. When any of this is on, that is 0, we'll get a 0 here. So if this is on, it will pass 0 and we'll get 0 here. And when this is 0, this will be off. And when this is off, no current flows to here and we will get 5 volts, that is 1. In all these cases, we will get 1. And in this final one, when both are 1, when both are 1, these both are off. This 5 volts will come here. It will turn on the BJT and we will have us in zero point 0.2 volts drop in saturation, which will be approximately 0. Will be 0. So this is what? This is NAND gate. Yes. So Renuka was correct. Yeah. Is there any doubt in these two? The analysis is clear. Uh, is it clear? Repeat. Okay. So let me draw fresh. So I have opposite. Okay. Let us see case by case. If I give 0 here and 1 here. When I give 0 here, that means that this diode is forward bias, right? So when this diode is forward bias, it will act as a short circuit. If it is a short circuit, this 0 will travel here. So here will be 0 volts. When here it is 0 volts, then this transistor will be off. Since it is 0 volts here, VB equals to 0, transistor is off. Now when transistor is off, current will not flow through this, and we will have 5 volts here. That is 1. Similarly, when so this is the case when any of these is on. So any of this is on 0. So whenever we give 0 at here at any of the terminal, one of the diodes will turn on. If any of them are on, these are ideal diodes. So they have no voltage drop. So it will be just a short circuit. And whenever we have 0 at the short circuit, we will get 0 here. That will turn off the BJT. And we get F equal to 1. That is why for all these three cases, we get F equal to 1. Now, if let's say both are 1, that means both the diodes are off. Now, if both the diodes are off, current will not flow through here. So this 5 volt we will get as it is here, and this transistor will be on. And when this transistor is on, current will flow through, all the current will flow through there here. And uh, in saturation, there will be very less drop here, approx 0.2 volts, which is in which we can consider as 0. Satyam, is it clear? Okay. So let us look at, so we have found this is what NOR, this is NAND. Now let us see what this is. Okay. Let us break it into some parts. So let us just see this part. Uh, Sorry, this part first. We'll see the rest later. Let us see this part. So what we have, let me try. This is X, right? Yeah. So if A, B, X, I want to find what is X for A and B. 0, 0, 0, 1, 1, 0, 1, 1. So as I said earlier, whenever this is 0 or any of them is 0, this will be forward bias, and this will get short circuit, and we'll get 0 here. So whenever any of them is 0, we'll get X equals to 0. When both of them are 1, both are reverse biased, we'll get 5 volt or 1 here. This is how X looks. Now we have some other circuit in front of it. Let me just show you again. I hope this is clear, this X part. Now we have some other circuit here also. Now let us look at this part of the circuit. I'll just draw this. Sorry, I was getting a call. Okay, so we had X here, and yeah, this is RD, this is RC. Okay, this is F. So we want to find F, right? So when we just have two cases, either X is 0 or 1, right? When X is, this is 0, both of these diodes are off. And when these diodes are off, uh, the current should not flow through here. And let me just, okay, yeah. When both of these diodes are off, there is no potential here, right? It will, so this transistor is off, and we get 5 volt here at F. So whenever X is 0, we get 1. When X is 1, this diode is on, this diode is on, we get 1 here, and there is some voltage difference here, VB greater than 0. Transistor on. When transistor is on, we get very less drop here, that is 0. So this is again a what is this, NAND gate. Is this part of the circuit clear? Yes, Dr. Danisha, all these are diode transistor logics. Okay. So now we have found NOR, NAND, and again NAND. So what we have now is we have a NOR gate, we have a NAND gate, and both of them are into NAND gate. Like this. And what are the input conditions given? VA is 0 and VB is 5. It is like 0, 1, 0, 1. So for NOR, we have written already, right? For NOR, when it is 0 and 1, output is 0. So here it is 0. For NAND, when it is 0 and 1, output is 1. Here it is 1. Again it is 1. So output is 1 equals to 5 volts. Is it clear? So it was a lengthy question, and I suggest you go through it again. Uh, should we go ahead? We also had a AND gate. No, sir. We did not have a AND gate, I think. We had NOR gate and NAND gate and another NAND gate. This is NOR, NAND, and NAND. There's no AND gate here. AND gate was in previous questions, I think. Yeah, previous question was AND gate. Okay, Prajwal, let us go to the next question. Third sub-circuit. What? Yeah, okay, fine. So, mm, yeah, let us find. Yeah, this part you can say is AND gate. this, and but this is only diode resistor logic, not diode transistor. Okay, let us see this question. In the okay, what is given? In the given circuit, find the value of V naught when VA VB equal to 0, VA VB equal to 5, and VA VB equal to 1. Okay, let's see case by case. When, let's say, first case, VA VB equal to 0. When both are 0, these diodes are on. We'll get 0 here. Okay, now we won't get 0. The voltage drop across this voltage will be 0. Okay, now here when this is 0.7, let's say this is 0, 0, then for this to turn on, the whole, either it will be on or off, right? Two conditions only. When this is off, V out will be 0. Now when this is on, this whole of 0.7 will drop across this to turn on this voltage. Then again, this V out will remain 0. So in the first case, we have V out equals to 0. Is this first case clear? Do you want me to repeat? Okay. Now let us look at the second case. Oh, sorry, I turned it off. First case, we got VO equals to 0. Second case, when V and VB are 5. It's 5, this is 5. Okay, when both are 5 volts. So both are off, right? So, okay. Now, then the circuit that we have, what it kind of looks like this, right? Uh, Let us ignore this part then. We have just this. Current will flow like this. Let's say current is I. Let us apply KVL. 5 minus I RH. Voltage drop is 0.7 minus 0.7 minus I RL equals to 0. So I RH plus RL minus I RH plus RL equals to 5 minus 0.7 plus, yeah. So I equals to 5 minus 0.7 divided by RS plus RL. And our V out is what? V out is IRL only, right? So VO equals to IRL. Will be RL times 5 minus 0.7 upon RS plus RL. And this is, RL is what? 10K, 4.3 upon 12K. So this will be 3.583 volt. So here we are getting V equal to 3.583. So just by elimination, you can see the answer is 1, right? But we can see the third case also. So is this case clear? Second case? So please let me know if you have doubts. I'll repeat this. I'll go move on to the third case. Okay, I'll get it. So in the third case, we have VA VB equals to 1. So if this is 1, this is 1. Okay. So here uh, it says it has 5 volt. Here it is 1. So if the diodes do turn on, let's say. So here we will have plus minus 0.7 drop. That means here we will have 1.7 volts at X, right? Now, if this diode turns on, we'll have 1.7 volt drop here. And so 1.7 minus zero point 0.7, we'll have 1 volt here. So V out will be 1 volt here. So answer will be A again. Um, do you have any doubts in this question? Sir, one second. Okay. How we got 1.7? Okay. So if we have 1 volts here, let's say, and we are having 5 volt here. So we say like the potential is higher on this side compared to this side, right? So this if these diodes may turn on, can turn on, right? Here it is high, here it is low. And it is said whenever the diodes are on, we have a potential drop of zero point 0.7 volts across them. So we have a potential drop of 0.7 volts here and 0.7 volts here. What does that mean? The so we have the plus and minus. So the voltage difference between Vx minus Va will be 0.7. Vx minus 1 is 0.7. Vx equals to 1.7. That is how we are getting 1.7 here. Now if Vx is 1.7, this diode may turn on. So again we will have zero point 0.7 drop. So let's say Vx minus V0 equal to 0.7. Vx is 1.7 minus V0 equal to 0.7. We'll give V0 equals to 1 volts. Is it clear? Siva? Okay. Let us see the next question. Consider the following circuit with A, B, and output V0. The logic implemented in the circuit is okay. So first of all, this is a CMOS logic, and no need to be scared by this. But uh, I think this is a difficult question for first time. But let us just see. So you see, all these blocks look very similar, right? They're all the same blocks, same kind of configuration of the transistors. So these are MOSFETs, first of all. So what does this thing is? So we have these two shorted and these two are shorted and these two are shorted. Okay. So uh, Dr. Yeah, Ashwin is saying, and Ashwini, it will be NAND. Yeah. So how can just see this that when transistors, just see the NMOS side. When transistors are in series, just multiply A dot B, and it will always give you an inverted function, that is NAND. If it was something like this, A, B, A, B, F, when these transistors are in parallel, right? In parallel, we do A plus B, and CMOS circuits always give inverted, that is A plus B bar. So this one is NAND, this is NOR, using CMOS logic. So you can analyze them easily, but I'm not going to analyze them here. Just make a truth table A, B, and F, and C 0, 0, 0, 1, 1, 0, 1, 0, 1, 1, 0, 1, 1. And what is F? I'll just do one case for example. Let's say it is 0 and 0, or it is NAND gate. Yeah, okay. So if this is 0, this is 0, okay. These two are off. There is no path for current here. This is 0, this is 0. Both PMOS are on. So one thing to note here is NMOS turns on when 1 is given, PMOS turns on when 0 is given. Okay. So we have these are both are on, and we will have this VDD at. So this is the only current path now, right? Here, this path is off. So we will get VDD at output, that is 1. Similarly, you can do the analysis for the other cases. You will get that this is a NAND function. Okay. Now let us see what they have drawn. So I'll just, we have 1, 2, 3, 4, 5. 5 NAND gates. I'll just draw 5 NAND gates first. 1, first one has inputs A and B. This one has one input is A, another input is this. Similarly here also B. Here it is like this, and here it is like this. Okay, so we have just seen this circuit, I think. This is XOR. So if you want to solve this, you get B bar here, and here you get A dot B bar whole bar, B dot B whole bar. Here you will get A dot A dot B whole bar dot B dot A dot B whole bar, and this will just negate this. Here you will get another bar. These two will cancel. We have dot A dot B bar dot B A dot B bar plus AB dot B bar plus AB B A bar plus B B bar plus A A bar B bar plus AB. This is not. I hope this Boolean operation is also clear. This is what just we did in one of the previous questions. Distributive property, what we call it. Anyway, just look over it once again. Let us see what we have next. Is there any doubt here? D is the answer. Okay. For a TTL circuit, the time that it takes to change the output from high to low is 25 nanosecond. Also, the propagation delay for the same circuit is given as 32 nanosecond. That is the output from low to high. Okay. So, so ideally, our waveforms are like this, right? There is zero time delay in going from low to high or high to low. Zero time delay. But that is not true. Uh, in practical cases, we have some delay, right? So this is T low to high, and this is T high to low. And the total propagation delay, TPD, is the average of these two. TLH plus THL by 2. Okay. So we are given that high to low time is 25 nanoseconds. So this is 25. Let's 25, and propagation delay is 32. This is 32. So we have to find TLH. So 32 into 2 plus TLH, sorry, equals to TLH plus 25. TLH is 64 minus 25, that is 39, right? So this was simple. Um, is this clear? Okay. You have to find the noise margin, transition width, and logic sign. You can see, we'll see what these are first. Okay. So, okay, there are two things, VIL and VIL and VIH. So VIL is the voltage that is required just at the edge of cutoff, and VIH is the, sorry, and at the edge of cutoff, what is the output is VOH, and in saturation at the edge of saturation, yeah, VIH and VOH. L. So VOL is output and VIH is input. So okay. So we know that it is giving VB sat is zero point 0.7. Sorry, yeah, VB sat is plus minus 0.7. So edge of cutoff means it is going from cutoff to saturation. So it will turn on just at 0 0.7. So 0 0.7 is the edge of cutoff, right? So our VIL will be 0 0.7. And one other thing that is given, VC sat is 0 0.2. So VC sat is this part is the output, right? This is VCE. In saturation, that is the edge of saturation, we will have the output VC sat equal to 0 0.2. That means VOL equals to 0 0.2 at the edge of saturation was cut off. Okay. Now we have to see, okay, when the transistor is still cut off, right? So the output here will be 5 volts, and if this is cut off, so for transistor to be turned on, we need greater than zero point 0.7 volts, right? So if when it is just at the edge of cutoff, when it is just 0.7, not more than that, then the transistor is still off. Then no current flows through it here, and this all 5 volts is at V out. So VOH is 5 volts. And one thing that we need to find is VIH. So, okay, at the edge of saturation, so I need a page. Let me add a page. At the edge of saturation, okay, I just draw this. So if we see IC, VC side we know is 0.2, so IC will be, okay, VCC, that is 5 volts. 5 minus, we know this is 0.2, divided by RC. RC is given, RC is 4 kilo ohms. 5 minus 4.8, 4.8 divided by 4k is 1.2 milliampere is IC. Now IB equals to IC by beta, that is 1.2 by 100 is 0.012 milliampere. Now at this time, what are we trying to find? We are trying to find VIH, right? When the transistor is at the edge of saturation, what is the input voltage? So this is RB. We know the current is 0.012. Okay. So when this is, if we apply K, okay, when it is on, we know that this will be at least zero point 0.7 volts, right? So when we apply KVL here now, so uh, VIH minus IB RB minus 0.7 equals to 0. VIH equals to 0.7 plus IBRB. 0.7 plus IB is what? 0.012 into RB is what? RB is 20 kilo ohm. That will give me 0.7 plus 0.24 up to 0.94. So this is VIH. So now we have all four quantities. VIH, VIL, VOH, VOL, 0.94, 0.75, yeah, 0.2. Yes. Okay. So what is, we have two noise margin, NMH and NML, noise margin high and noise margin low. NMH is VOH minus VIH. This is VIL minus VOL. So if you see what is this, this is 5 minus 0.94. This is zero point 0.7 minus 0.2. This is what? 4.06 and it is 0.5. So our noise margin will be the lower of these two, that is 0.5 volts. Okay. Now transition width is VIH minus VIL. I'm just writing all the formulas so you remember. It is 0.94 minus 0.7 equals to 0.24 volt. And last is the logic swing. That is the difference between the outputs. So transition width is like the what is the width of the voltage that will cause the transition, and logic swing is the what will be the swing at the output when the uh, transition takes place. That will be the difference of the outputs. It is 5 minus 0.2 plus to 0, sorry, 4.8 volts. So answer will be this one. Is it clear? Okay. Okay, I'll just quickly solve this question also. So it's already late. You guys must be tired. I'll solve it quickly. It says when VA is 0 and VA equal to 5, what is the uh, voltage at the output? Okay. When we have 5 volt as the input. Okay. So when this is 5 volt, VB is so when this is 5, this can actually can not be 5 actually. It will be less than 5 only, right? Voltage here will be less than 5. This transistor will be off. And when this transistor is off, just a minute. Yeah, when this transistor is, oh, sorry, this junction is reverse bias. And when this is 5, like when here it is high voltage, it will be forward bias. So we will have some voltage here. Now, what it will do is it will turn on this transistor and also this transistor. So this will be on, this will be on, and what we will get is, and this is on, VC set we know is 0.2 volts. So when VA is 0, VO equals to 0.2. I'll repeat this. I did it within my mind most of it. So this is 5 volts. We know Here will be, let's say, some if even if some current flows, it will be, let's say, 4 point something x, right? Because the peak voltage is 5, it cannot go more than 5 to turn this on, right? So here this is reverse bias. And since there will be some positive voltage here, it will be forward bias here. That is this. So if we take it as this configuration 5, yeah. So this is forward bias, this is reverse bias. That is 5 here. So this 5 will reach here. When this 5 reaches here, this transistor will turn on. Here VB will be higher, so this transistor will turn on. So again, let us suppose if we take this diode model, this 5 volt will go here. Actually, this 5 volt will come here. When the whole current will flow here, and this 5 volt will appear here. So only zero point 0.2 will drop here. Rest 4.8 will drop here. So I'm just taking it as 5 volts still. This 5 volt will appear here. I'll just look. Let me just write 4.8 itself, not to confuse you. This zero point 0.2 volt will drop here when this is on. Rest out of this 5, some voltage drop will be dropped here, and let's say 4 point something is dropped here. Now again, since this is 4 point something voltage difference here, this transistor is also on, and when this is on, we know that VC set is zero point 0.2. That is why VO is zero point 0.2. Okay. Okay. So next thing is okay. Take the next case when VA equals to 5 volts. Okay, we took 5, right? Sorry, 0. Took 5 volt case. Now I'll take 0 volt case. When this is 0, this will be forward bias, and I think this will also be forward bias. This is forward bias. This will be forward bias also. This will not be forward bias. So if this is 0, this 0 will reach here. So this 0 will reach here. If this is 0 here, so then this will be off. And when this is off, this will also be off. And when this is off, we'll get some this. There's no path for the current for flow exists except this, right? Okay, this can also turn on. So we will get VA equals to 0 volt equals to. Okay, now we need to apply KCL here, right? We cannot directly say what will be the VO here since we have this transistor also. So let me write KCL 5 minus 130I plus, let's say this transistor is 0 on. So when this transistor is off, this whole 5 volt will come here, right? Since no current will be flowing through here, this 5 volt will be here. So this transistor will be on. So here will be 0 0.2 minus 0 0.2. The diode drop we know is how much? No, diode drop is 0.7 minus 0 0.7 minus VO equals to 0. VO equals to 5 minus 5 minus 0 0.9 into, sorry, minus 130. 4.1 minus 130i. Also, V is also equal to 5k into I. Same current is flowing here also, right? Into I. So 5000 I equals to 4.1 minus 130i. So, okay. Uh, if we solve this, we'll get I is approximately equals to zero point 0.8 milliampere, and VO will be 5k into 0.8 is 4 volts. So VO will be 4 volts. So this will be our answer. Is this clear? Okay. So I'll do the last question today. It is very simple. So it says the that in the TTL open collector circuit below, IOL max is 16 milliampere. What should be the minimum value of resistor R to prevent the damage? The V is 5. Okay, this is 5 volt. It doesn't matter. We are saying IOL max is the 16 milliampere. So what IOL max is? Max current through the output load, or here load is what? This C is the load, right? C C junction. So given that this the current flowing through here is how much? 16 milliampere. We know when this current will flow only when this is turned on, and when this is turned on, it will be zero point 0.2 volt drop. We see. So we just have to find R. So 5 minus 16 R minus zero point 0.2 is to 0. R equals to 5 minus 0.2 by 16 milliampere. This will give me 300 ohms. So, any doubts in this part? Um, do you want me to repeat anything? Okay. So, I went through fairly quickly through the last couple of questions due to lack of time, but I'll upload the video on YouTube, and I recommend you to go through that once. So, if you still have any doubts, you can please comment on the YouTube video, or you can just email me. I'll try to reply you as soon as possible. Okay. So let us close the session today, and thank you for joining. Thank you, everyone.